Ladies and gentlemen, welcome to the 2017 Optical Fiber Communication Conference and Exhibition. Please welcome OFC General Co-Chair Peter Wisna, Nokia Bell Labs.
Good morning. On behalf of my co-chairs, Shuna Miki and Andrew Lord, I welcome you to Los Angeles and to OFC 2017. More than 13,000 attendees have gathered in Los Angeles this week to experience the latest innovations, breakthroughs, and technological advancements from leaders in the optics community at the largest optical communications conference in the world. And everybody in this room shares a common vision and a common goal: to scale an invisible optical infrastructure into the next decade and beyond. An infrastructure that underpins our communications and information society and that accommodates an ever-increasing number and wealth of applications and services. That's an incredibly challenging and rewarding task. This morning, we are excited to have three outstanding plenary speakers who will offer their insights into the coming innovations in optical communications. Google's Senior Vice President for Technical Infrastructure, Urs Hölzle, will talk about the transparent networks that the ubiquitous cloud requires. Then Professor Smit from the Eindhoven University of Technology in the Netherlands will discuss fabless photonic integration platforms and the diverse range of applications and opportunities that they open up. And finally, Professor Mischa Dohler from King's College London will present on the Internet of Skills, where communications, robotics, and artificial intelligence merge. As you can see, we also have a piano on stage here today. That's because Mischa is also a gifted musician, and he will integrate music from his latest album right into his plenary talk. That's a first at OFC, and next year's chairs already said they will have a tough time. They'll have to bring up an orchestra to top that. So before we bring up our speakers, I would like to take a minute to highlight some of the main program events and sessions that are planned for this week. The exhibit hall opens today, immediately after the conclusion of this session, and will stay open until 4 p.m. on Thursday. Close to 650 exhibitors from over 60 countries are part of this year's exhibit, showcasing the latest products, technologies, and equipments across the entire supply chain for optical telecom and data centers. While on the exhibit floor, you can also participate in several show floor events. The Market Watch, which is sponsored by Huawei, is a 3-day series of panel discussions covering the latest application topics and business issues in the field of optical communications. The Network Operator Summit, formerly known as the Service Provider Summit, is a dynamic program presenting inside perspectives from service providers and network operators, discussing their planning, deployment, and operational issues, and explaining the drivers that are behind their network requirements. The Network Operator Summit is sponsored by Juniper and features 2 panel discussions and a special keynote address from Zhenyong Zhang, Vice President of China Telecom Beijing Research Institute. The new OFC Career Zone Live provides an opportunity for job seekers to network and connect with potential employers and recruiters. The Data Center Summit this afternoon starts at noon, or 12:15, in Expo Theater 2, and culminates in the SDN NFV Demo Zone at 4:30 in the 400 foyer. The demos shown there will provide attendees with a chance to view live pre-commercial proof-of-concept implementations from 15 different presenters across industry and academia. Now to the program. About 1,100 technical papers were submitted to OFC this year, with 30% coming from Europe and 40% from the Pacific Rim. So that really demonstrates the truly global nature of this conference. In addition, this week will feature 11 parallel sessions comprised of nearly 450 contributed oral presentations, 20 tutorials, and about 130 invited talks. Over 120 posters will be presented during 2 poster sessions, which begin tomorrow at 10 a.m. on the exhibit floor. We'll also have 2 symposia and 6 panels on exciting hot topics of our industry. On Sunday and Monday, you already had the opportunity to participate in 10 workshops and a wide range of short courses. We had 14 new short courses this year, an expert taught portfolio that covers the entire topic areas of OFC. If you missed that, you have to come back next year already on Sunday to participate in that kind of program. In addition, this year's OFC features a special smart city competition based on a fictitious city getting ready to celebrate its 700-year anniversary in 2023. 4 teams have competed and recommended optical solutions and technologies to be used for broadcasting the city's special anniversary events. 2 distinctions were given this year to Team Terrapolis and Alive. Congratulations to all participants. Our annual rump session will take place this evening, where the topic will be how and when will fiber replace copper in the data center. The rump session is always a highlight of OFC and aided by some beer and wine that will be provided and moderated by some of the most provocative folks within our community. People tend to discuss much more freely and openly at that session than at a typical conference session. You'll have lots of fun there, so be sure to attend. Just before the rump session, we'll have our conference reception tonight at 6:30 in the concourse hall, to which I would like to cordially invite you all. The reception is a great opportunity to connect with old friends and to meet colleagues from around the world. Sienna's OTN Speedwagon Band will perform right at the reception. The conference concludes on Thursday with the post-deadline papers from 6 to 8 p.m. And as you all know, these are the hottest topics, the newest results, the new records that are set in our industry. So be sure to circle that into your calendar. You can find many more details in the conference program, as well as on your smartphone using the OFC 2017 app. The app contains key information about events being held throughout the conference, including direct access to the conference papers. While you have your phone out, be sure to check the app and also take the opportunity to engage with other conference attendees and exhibitors on social media using hashtag OFC17. You can also get the latest updates on the conference and special events by following us on Twitter at OFC Conference. Now, putting together an event like OFC is an enormous task. Over 200 volunteers have taken time out of their busy day jobs to put together the kind of outstanding program that we are pleased to offer you here. In addition to chairing sessions, organizing workshops, and driving the invited program, collectively they have provided well over 10,000 reviews for the papers that were submitted to OFC. A big thank you to all of you on the TPC for your hard work and dedication to this conference. The Technical Program Committee is led by our 3 fantastic technical program chairs. On behalf of the general chairs, I would like to give a special thank you to Gabriela Bosco, Jörg Peter Elbers, and Laurent Charest for the amazing job that has shaped the technical program of OFC 2017. And a huge thank you goes to our corporate sponsors, media partners, and the OFC conference co-sponsors, the Optical Society, the IEEE Communications Society, and the IEEE Photonics Society. Their support allows us to put on the amazing conference that we do. And last, but certainly not least, thank you to the hardworking staff that supports the conference behind the scenes all year round. They begin working long before any of us arrive here at the venue, and they keep going long until everybody has headed home. Their efforts keep things running smoothly, and at this point, they have already locked in venues out until 2025 and have started with initial technical program planning for OFC 2019. Again, thank you all for your efforts. It's now my great pleasure to introduce our first plenary speaker. Urs Hölzle is Google's Senior Vice President for Technical Infrastructure. Urs has been with Google nearly from its start, as he was their employee number 8. As the VP for Technical Infrastructure, he oversees the design, installation, and operation of the servers, networks, and data centers that power Google services. Under his leadership, Urs and his team have implemented efficiency innovations that have reduced the energy used by Google's infrastructure to less than half of the industry average. Prior to joining Google, Urs received a master's degree in computer science from ETH Zurich and a PhD from Stanford University. At Stanford, and then with a startup company, Urs invented the fundamental techniques that are used in most of today's leading Java compilers. Before joining Google, Urs was also a professor of computer science at the University of California at Santa Barbara. In 2007, Urs co-authored the book, The Case for Energy Proportional Computing, which has spurred computer manufacturers across the industry to create more energy-efficient devices. Urs has been recognized with several awards and honors. He is a fellow of the ACM and is a member of the Swiss Academy of Arts and Sciences and the US National Academy of Engineering. He is also a board member of the World Wildlife Fund. Today, Urs will discuss his work at Google in building the cloud infrastructure that creates a network unparalleled in reach, scale, and capability. Please join me in welcoming our first plenary speaker, Urs Hölzle.
All right, thank you very much. It's definitely a big honor to be here, and I hope that I leave you with some interesting thoughts from the perspective of a large user of optics, but also a builder of systems, since we build a lot of the things that we actually operate. Before I start, I just want to thank the really excellent team that we have at Google. So none of what I'm talking about is really my own work. You find many of them here. I think we have about 30 attendees, and there's also additional talks that go into many of the topics that I'm going to touch today. So if they pique your curiosity, then look in your program book. So my main job today, though, is to convince you that while things are pretty good right now in the optics industry, that they really need to change. And I'll tell you why. The main thesis here is that incremental improvements aren't going to work because we're in a period where we see 10x growth in pretty much all of the markets in relatively short time frames, 2-3 years, right? So it's not about 30% growth year over year. It's about a factor of 2 growth year over year, and I'll tell you some more details. And that's true in a data center, where it's driven by disaggregation, so the separation of compute and storage. It's also true at the campus and metro level, where you connect multiple data centers together to do storage replication or to actually get to the rest of the internet. And it's true in a wide area network to deliver all these applications to end users, be that video, photos, et cetera, et cetera. A little bit of history. So I'll first kind of tell you how we get into that, and then really what we are looking for. How we got into that was that for the last 15 years we've been building infrastructure at a fairly large scale, and we've been doing that because we had to, because we couldn't buy the products that we really needed to operate. And the reason was that even 15 years ago we had a huge computational problem searching the web, with a lot of traffic. We're the #1 search engine even back then. And to actually handle that computation, we just could not use standard gear. It would have been far too expensive and far too limiting. And so we started with the servers and a cluster architecture to try and find scale-out architectures. And along the way, we had to reinvent quite a few of the ways how you do things. And this wasn't because we were in a particularly innovative mood or because we were particularly smart. It was really because we had a gun to our head that basically said, if you do it the old way, you're going to die, so think of something else. Right? And so a lot of the things that we've did really are born out of necessity, and you'll see that later on. That is still true today. Just to give you some numbers about Google. So today you have a billion hours of YouTube videos watched every day. For those of you who could do math, that's 10,000 hours every second. 100 billion searches, well over 100 billion searches every month. And a billion IP addresses that Google Cloud customers, so not Google, but Google Cloud platform customers connect to every single day. Right? And in all, this infrastructure actually supports 7 applications with a billion or more users. So the searches, the Gmails, the YouTubes, the Androids, etc., etc. So to do that, we had to innovate. And this is a brief overview of the software side of it. It started with GFS. It stands for the Google File System. We had to build that to really store the copy of the web that we had, crawled from the web and then needed to actually index and then serve, right? And there's way too many disks. Disks are failing all the time. We couldn't use standard sort of filers or so because they were far too slow and too expensive per byte. So that was our first sort of deep innovation. But throughout the years, this touched really many areas. I want to just highlight a few things like TensorFlow, which is all the rage right now to better express machine learning computations. And then on the networking side, same story more or less. We started with a cache, a CDN for YouTube basically in 2006, and lots of other pieces, both hardware and software. So for example, Watchtower was our first fabric, data center fabric that was deployed at scale. It was really the second, but the first one only went to a few 10,000 ports or so. So it's the first one at scale. Jupyter is another one. Onyx was our first SDN controller based on OpenFlow. B4 was our first SDN WAN backbone. And even more recently, you see BBR or quick improvements to internet protocols that make the internet faster for everyone. So it's been lots of work, all of it really coming out of the large problem space that we are seeing, and that often is kind of running away from us and really running away from the sweet spot of existing solutions. And so you have to find something new to solve that. Here's another quick overview of the hardware side. Way back something like 2006-ish or so, we were in a 4-post commercial cluster network, so four chassis that tried to connect a bunch of computers. Firehose was our first rework of that, really the first in-house hardware. We learned a lot from that. 1.0 was terrible, 1.1 was kind of practical, but we fast followed with the first real fabrics, and then Watchtower, Saturn, and Jupyter, all basically what you know today as fat trees with petabits of bandwidth sort of inside the building. It's definitely served us pretty well, and now has become more standard. So it's actually a place where it's plausible to use standard gear to compose these systems. Our global network, just to give you a brief overview, kind of spans pretty much everywhere. This is a simplified slide. It has not just the on-net, so the blue points are kind of the on-net ones, and we have 150 or so countries with an on-net present, with a physical presence. But then we have thousands of cache locations, the yellow points, where our CDN is running. So that's where you get the more popular YouTube videos, etc. from. And then, of course, that network is used to connect data centers Here's a footprint of where we are today with the Google Cloud regions that are also, again, pretty much anywhere, and they're connected by this backbone. So when I say cloud, I want to clarify a little bit, because cloud kind of means different things at different times. And the way I think about it is cloud actually started, so in a 1.0 period, with basically co-location, right? So co-location, the late 90s, the early 2000s, let you rent a building instead of building it yourself. And with VMware, etc., it also first brought the concept of virtualization to the masses, from the mainframes to the masses, so that you could reduce your CapEx in the enterprise. And then Cloud 2.0 was what is sort of today's cloud platform. So you rent not just the building, but you also rent the virtual machines and a bunch of services on top of that. And so you administer virtual hardware, so to speak, virtual networks, instead of having your on-premise physical hardware, physical networks. But fairly quickly, we're actually moving to a Cloud 3.0 environment. And in 3.0, you don't even see the servers and the networks anymore. So for example, on Google Cloud Platform, when you use App Engine, your application is really run by the App Engine control plane, and it may change zones or regions without you taking any action and without you noticing. It's because you never start really an individual instance. And so auto-scaling, placement, global placement, replication is all just built in as a service, and you never ever see a VM or a server or a disk. Similarly, BigQuery, our data warehouse and analytics platform, you don't dimension a cluster to run this on. Right? You basically provide the data and then the query, and then the query runs on your data, and we pick the number of machines and what kind of machines there are, etc. So it's really serverless, and the big advantage of that is that you outsource your infrastructure to us. You don't have to worry about operating system patches and machine dimensions, etc. And also you really get scalability on demand, so you only pay for what you're using, and you don't have to have a system administrator anymore for that. So now, for Cloud 3.0 to actually work, behind the scenes, you need to have a very, very good network, and that's where I'm going to spend the rest of my talk on. Why am I saying that? Well, if you have a good network, then you can actually keep up certain illusions that are really important for serverless computing to work, right? Because you're basically telling the user, just give me the problem, don't worry about its location. Just give me the data, don't worry about the compute that you're doing on it. But in reality, between those things is a network, and if that network isn't sufficiently ubiquitous, sufficiently high performance, high capacity, then the user will actually discover that the illusion you promised them is not real. And then they can't do anything about it because it's serverless, like I can't actually influence it. Right? So it's very, very important to have a network that's ubiquitous, that's really high capacity, and that's very high availability behind the scenes. Right? You don't explicitly manage that network anymore as a customer, but it's very important for it to be there, because otherwise you will notice problems. So before I was saying 10x, here's a slightly abstracted graph, but a real data underneath of the intra data center bandwidth growth, so the bandwidth inside of our data centers. And basically what you'll see is that in a period of 6 years, it goes up by a factor of 50, and the curve, by the way, continues like that, right? So 6 years, factor of 50 is roughly a factor of 2 every single year, right? So this traffic has been doubling roughly every year. And that's been true for more than just the 6 years that you see here. And that's why I'm saying we really need to move away from the incremental sort of approach to one where we are looking for step functions, where we're looking for 10x improvements. Because if you have a doubling every year, 10x is only 3.x years away, right? So you don't have that much time to get your product to handle that 10x. So how do we do that today? Well, first, just to make sure everyone understands what drives that 10x, right? So the disaggregated data center on the left is basically one where the storage devices, disks and flash, are connected to the network as well as the compute devices. You know, the CPUs, the GPUs, etc., are also connected to the network. And obviously, these two work together, and so the network in between is, if you want, the storage area network. But in the modern data centers, you don't have a separate storage area network and a separate IP network. It's all the same network. But that really drives the bandwidth. Today, our current model is to use the pluggable optics. You see that on the upper right. I mean, you plug them in front of every switch. It's working, but it's really bottlenecking what we can do, because of both the power and the cost of that solution is really just on the edge of what's still plausible. And for example, a density that you can get is already too low. So we'd like to move to something that is much, much more compact, cheaper, and also more sort of industrially manufactured, so to speak. Right? The optics industry today is still a little bit of an artisan craft, so to speak. And if you really want to get 10x multiple times and get both the scale to work and the costs to work while still having a margin, you got to automate that. And so we're very much looking forward to a model that looks more like the rest of the data center electronics, right? The chipsets, etc., that are really manufactured in a highly automated way. Now, give you some more ideas about 10x. Here's a picture of one of our data centers, and here's a duct bank that leads from one of these buildings to the next building. And you can obviously see there's a lot of ducts there, and actually each of these ducts contains not a few fiber strands, but typically multi-fiber cables with 3,500 strands in there. And the key point I want to drive home is that we're not building this to cover the next 20 years of growth, imagined in our buildings. We're building this because the first duct bank that we built is full, and we needed a new one, and we don't expect that one to last, definitely not a double-digit number of years, maybe 5 years if we're lucky. So fiber at scale really happens today, and at that scale, a lot of things kind of break down. Imagine, for example, wanting to terminate, tens of thousands of fibers at once, right? Because, there's a ton of fiber in there. One layer is probably 50, 100,000 fiber pairs. So you need to terminate them on the other side. The existing way of terminating fiber just doesn't work. Right? So please build me a robot that terminates fiber. And by the way, it's perfectly okay if that robot only gets it right 99% of the time. That's just fine, right? Because it's not like 99% of this wouldn't be useful, right? So that's actually a common topic. It doesn't have to be perfect, right? It doesn't have to be perfect. It has to be, on average, very good, because you see the law of average is obviously at the scale. But the key point I want to drive home is this isn't like some envisioned future where if everything goes right, the demand goes up. This is happening today. We are facing these problems today, and so I'm not talking to you about imagined problems. Now, terrestrial links are reasonably well understood. You can upgrade them. Submarine links are a little bit harder. And for the submarine links, they really are important because a global cloud is not possible if you can't get your bits anywhere in the world. And 70% of that world is water, so submarine links is a big component of that. And actually, because of the worse economics, it's a sizable cost component of that global backbone. And there's really two parts in here that matter. One is the optics, and then the other one is just the general wet plant, the cable, the power, everything. So give you an idea, here's we're right now building our third cable across the Pacific. So Google's been building cables for 10 years, roughly, to satisfy our capacity demand. So right now we're on the one on the right. I want to give credit to everyone who's worked on that, and really kudos. Coherent optics have been a lifesaver, right? You know, that's why you see the cable going from 5 to 144 terabits. So the same trend that's been happening on the terrestrial optics also is playing out in submarine optics, where it's arguably even more important. And so I'm very happy that we're now on Gen 4, I think, of coherent optics, and that the development still is progressing. So really kudos to whoever of you works on that. That really makes a lot of things possible that are just unthinkable otherwise. Having said that, please keep it up, because a factor of 10 is coming. And so we really need to have a curve that works. More importantly, though, when you look at the needs of a content provider and global cloud provider like us, you actually never want to buy a cable, right? So traditionally, submarine cables have been built by maybe a small consortium, and they're super, custom and super highly reliable and super expensive, because nobody wants that cable to fail. The problem is that really doesn't give you 5 nines. It doesn't even give you 3 nines, because the repair times are too long and you can't really protect against the ship anchor. So what you really want to do is something that's more similar to the data center, where you say, can't we have cheaper cables, maybe lower capacity, but we have multiple cables that are physically separated, right? Because basically with every additional cable, you exponentially decrease your failure amount. And also, if you have n cables, and let's say you have n plus 1, so you have one extra, one can fail, that actually gets cheaper as n goes up. So in reality, if we could buy it, we would rather have 30 cables across the Pacific, not 3, right? It would be a much better solution for us. But that means that the wet plant really has to be rethought to be much cheaper, maybe less ambitious, but if you're one of 30, then that will work just fine. As an aside, cable building in the last 150 years hasn't really changed that much. So marine operations, that cable itself, actually are still surprisingly similar. Obviously, the inside, copper versus fiber has changed enormously. But as a whole, it's been a very, very stable industry. And so with new materials, new approaches, et cetera, hopefully there is some oomph left here. Now let me switch from the hardware to the software, because there's a remaining very important point. And that is that all of this stuff that we build in our network needs to be programmable. And I'll explain to you kind of why that is. So in a conventional network, when you had different layers, right? At the top, you have sort of the overlay network, the virtual networks, et cetera, then the IP network, then the optical layer. In the past, the network didn't know what the applications on top of it were doing, and the applications didn't know what the network was doing, right? And so something went wrong at the network layer. You kind of try to hide it and pretend that everything's still fine. And if something goes wrong in the application, network doesn't know, so it's not doing anything, right? That isn't really a great approach, because if you want to get to 5 nines, let's say under n plus 1 or n plus 2 failure, you kind of need to guard against relatively tail end events, right? The worst 2 links failing and things like that. And if at that point you have the option of also changing things at the application level, not just changing things at the network level to compensate, then you can be in much, much more cost-efficient sort of parts of the design space, right? Now, to do that, you got to have something that is service-aware, so it actually understands the services that are running on top of it, that has APIs that give you access to, that make you understand the APIs. You have to have the programmability, and you have to have the telemetry to kind of understand what's going on. And I'll show you 3 applications of that. If you have this, what you can do, just to really drive home how important that is. So the first one is a choice between network and compute level redundancy, right? So what should you do? Where should you pay money for redundancy? When you have a network, typically people think about, oh, I got to make this network redundant, so let me simulate taking away each link and each node and maybe 2 nodes at a time, and how much extra capacity do I need to still be running even when failures happen. But in reality, the applications that you run on top of this network and the data centers are also n+1 or n+2. Right? So you're kind of trying to keep a perfect network underneath something that itself is n+1, n+2. And so you're paying twice for the n+2. Whereas if you have that connection, if you have the visibility into your network, then if something bad happens, you can react to it perhaps at the application layer by reprogramming your load balancer by putting more traffic on the East Coast, therefore removing the demand on a link where an element failed. Right? So you have much faster and much cheaper ways to provide your resiliency. The second one is, that overlay can be provisioned on demand. If you understand where your capacity is, if someone walks up and says, hey, I would like to have connectivity to Google, then we can provision that link dynamically in an automated way without needing to go replug things or log into servers or routers or optical equipment and kind of do manual commands. So you have very rapid updates to that topology as new customers come online. And then last but not least, when you actually have a physical failure at layer 1, right? So something goes wrong in a network at the bottom. If you understand the network and the application, you can plan for repair actions and automatically program them into the network much faster than you typically can, and also much more optimal because you see the whole picture. You don't just see the local picture with the link failed. So you can route traffic around, etc. And so with your optical backbone being programmable too, the whole system that actually connects the network and the applications together can figure out the best path to restoration and then program a few elements to implement that new path. And it will find a better solution than your local gear would because it has more information, and it does it faster than the actual physical repair. So you have restore times that are maybe in low minutes or maybe even under a minute versus the physical repair that may take hours or even days in the submarine case. All right, so to summarize, what I'm excuse me, what I'm trying to leave you with is really 3 things. And I hope that I've convinced you that things are, have been pretty great in the last 5 years, right? So things are going well, but really we're kind of rapidly approaching a wall, and we got to find a way to take off and skip that wall rather than crashing into it. The first reason is that the cloud-driven sort of disaggregated architectures really drive bandwidth demand, and enormous bandwidth demand, both in the data center, in the metro, and then divided down by that factor, but still a annual similar growth rate at the long-term links. So we're really looking for things that are step function changes, not incremental changes. Second, what are the implications for the industry, for the networking industry and the optical industry? Well, clearly, for the last few years, operators like us have driven a lot of growth in pretty much all of these segments, right? From data center optics to submarine building. There's really been a renaissance of CapEx, if you want. And at the same time, we pushed for more innovations, more automation, more R&D, and really lower unit costs. Because if you're in a place where your demand goes up by a factor of 2, you really got to stay ahead of things, and you can't work the same way. I expect that really with the Cloud 3.0 approach that's delivering a lot of value to customers, this trend will accelerate. And so we need to get to an industry where a factor of 2 isn't a problem. And that's like the chip industry, where you can manufacture things in a highly automated way. And last but not least, I think I want to really urge you to, if you haven't already, to embrace the software-defined network at the optical layer 2. The market, certainly from the highest hyperscalers, will go to those whose gear is programmable. And programmability doesn't mean that you give us your beautiful control plane that handles everything automatically, right? We actually don't want that. And that's not because we have a more beautiful control plane. It's because we have a different control plane that couples the optics and the IP and the application space, right? And those are the ways how we want to do the actual control, right? And so we can't use your beautiful control plane that is optical only. You might still need to build it for other customers, but just don't expect hyperscalers to appreciate it, right? Even though I'm sure you did great work. So with those thoughts, I hope you are jumping out of your seats and saying, I want to reduce costs by a factor of 2 every year and my capacity by a factor of 10. And of course, it's all software programmability. So thank you very much.
Thank you very much, Urs, for this great and inspiring talk. So if anybody in this room still believes that the capacity crunch is not happening, then you must have been sleeping for the last 30 minutes. It's now my pleasure to bring up my general co-chair, Shuna Miki, who will introduce to you this year's Tyndall Award winner.
Thank you, Peter. The John Tyndall Award is one of the highest honors in our industry and recognizes outstanding contributions to fiber optics technology. The award is named for the 19th century scientist, John Tyndall, who was the first to demonstrate the phenomenon of internal reflection and is dedicated to his memory and contributions. The award is co-sponsored by the IEEE Photonics Society and the Optical Society, and supported by Corning. As part of the award, Tyndall recipients receive a scroll, an honorarium, and a specially commissioned crystal sculpture that represents the concept of Tyndall's total internal reflection. Today, we are honored to present the 2017 John Tyndall Award to Professor Evgeny Dianov. Since 1974, Professor Dianov has been involved with most aspects of fiber optics, including fiber fabrication technologies, fiber measurements, nonlinear fiber optics, soliton propagations, fiber lasers, and optical amplifiers. His research in the field of low-loss optical fiber yielded very notable results, including advancing the optical design, transmission, model characterization, nonlinearity, and the dispersion of a wide range of optical fiber compositions. Several of the advancements realized by Evgeny and his team were first to the world and possessed record performance attributes, and his contributions have significantly advanced fiber optic technologies. He has published more than 700 scientific papers and patents. He received the 1974 State Prize of the Soviet Union for neodymium glass lasers, and in 1994 became a full member of the Russian Academy of Sciences. The Tyndall Award is a fitting tribute to Evgeny's passion, determination, and groundbreaking research in nonlinear fiber optics and optical fiber amplifiers. Please join me in welcoming the 2017 Tyndall Award winner, being recognized for his pioneering leadership in optical fiber development and outstanding contributions to nonlinear fiber optics and optical fiber amplifiers. Professor Evgeny Dianov.
Dear Professor Shunamiki, dear colleagues, ladies and gentlemen, I am happy to get John Tyndall Award, and I'd like just to thank those people who nominated, supported, and selected me as for this award. I should say that it is a great pleasure for me to deal with fiber optics for more than 40 years. And I am very grateful to Nobel winner, academician Prokhorov, who in 1973 suggested me to develop low-loss optical fibers in the Soviet Union. And the experimental work on development of such fibers were launched in early 1974, and in 1975 we obtained first low-loss optical fibers. The history of development of low-loss fibers in our country is quite interesting. The happiest period was the years the 70s and 80s. We had very good financing of fiber optics researchers by Soviet government. We created very good team of researchers, very young and talented researchers, and we managed to get very good results in this period in developing various low-loss optical fibers and in fundamental researches of these fibers. The next period, it was some perestroika. I think you know this word. And in this period, we have wider opportunity to collaborate with foreign organizations, and many well-known companies showed great interest in our results. So we had more than 10 contracts in this period with such company as AT&T Bell Telephone, Corning Glass, Bell Northern Researchers, MPB Technologies, Samsung Electronics, and other companies. And these contracts were very useful for us because we got a lot of practical information concerning application of fibers. Unfortunately, I can say so that in this period, many our researchers went abroad to work, and in the next years, I had main task first to strengthen fiber optics research centers by new talented researchers, and then just to find new promising directions in fiber optics researches. And I think we have solved such tasks quite successfully, and I hope that you're familiar with our results concerning Wismut-doped optical fibers, hollow core fibers, and some other results. So, finishing my remarks, I should say that I'm very grateful to my wife. She is here for the constant supporting me. Thank you very much for your attention.
Congratulations again to Evgeny on this prestigious achievement. And now it's my great pleasure to introduce our second plenary speaker this morning, Professor Meint K. Smit. Meint graduated with a degree in electrical engineering in 1974 from the Delft University of Technology in the Netherlands, and then achieved his PhD in integrated optics in 1991, both with honors. His notable achievements include inventing arrayed waveguide grating, which considerably increased the transmission capacity of optical networks. His work and impact was recognized with the LEOS Technical Achievement Award in 1997. Meint was also closely involved with the introduction of multimode interference couplers in semiconductor-based photonic integrated circuit technology. In 2000, he became the leader of the photonic integration group at the Cobra Research at the Eindhoven University of Technology. Currently, his research interests are in indium phosphide-based photonic integration and integration of indium phosphide circuitry on silicon. He is the founder of the JEPIX platform, the Joint European Platform for Photonic Integration of Components and Circuits, and is strongly involved in the development of the indium phosphide-based photonic foundry system in Europe. He is an IEEE Fellow, and he received an ERC Advanced Grant in 2012. Today, he will describe the photonics foundry model and its development in Europe, including the significant reductions in prototyping costs and the broad range of potential applications. Please join me in welcoming Meint K. Smit and his presentation, Photonic Integrated Circuits for All, how foundries are transforming the prototyping of exciting new devices.
Yes, thank you for this introduction. Good morning, ladies and gentlemen. Yes, so my presentation is about how we can reduce the costs of development of photonic integrated circuits in such a way that they become also accessible for smaller companies and for academic research. So my first slide is about what photonic integration is. It is the classical slide of Infinera. Here you see one channel from a WDM transceiver, and the channel contains a handful of optical components. And if you have 10 of those channels, you have a desk full of optical components. And the strength of photonic integration is that you can integrate all those components in one or two chips. And the advantages are evident, so it saves you a lot of packaging cost. It's much smaller, it's more robust, because you can integrate a lot of components, you can integrate more functionality, and in large volumes the manufacturing costs are lower. There's also a disadvantage, and that is you need an expensive fab and an expensive process, so the entry costs are high, and this is where generic integration comes in. Well, generic integration technology is actually, we copied it from microelectronics. In microelectronics in the beginning you had a lot of different processes, but it converged to a few CMOS-based processes, and in those processes you have a few basic building blocks, transistors, resistors, capacitors, with a few variations, and even the most complex chips consist of this very small set of basic building blocks. And in photonics we can do something similar. So light has an amplitude, it has a phase and a polarization. So if we have building blocks for manipulating the amplitude, the phase and the polarization, then we can support a lot of functionality. And here you see the schematic cross-section of the components that we developed at the Cobra Research Institute. So we integrated all those basic building blocks in one integration process. Here you see what it looks in reality. Now, if you have a process with these basic building blocks, you can make a lot of things. So with the passive devices, you can have couplers, demultiplexers, and you can do all those passives in any material, actually. You can do it in indium phosphide, silicon nitride. But then if you add a phase modulator and you combine that with the passives, you can also make amplitude modulators, fast space switches, and all kind of WDM components, cross connects, air drops. If you want fast modulators, then you are restricted to indium phosphide and silicon. Both support fast modulators. And then the third important building block is the optical amplifier. It's the workhorse of photonic integration. You could call it a transistor of photonics. If you have the amplifier, you can make a lot of different lasers. Fabry-Perot lasers, tunables, multi-wavelength lasers, also picosecond pulse lasers. So that's the strength of indium phosphide, that you can have this very powerful component integrated in your chip. So it's like kind of Lego system. Once you have a box with nice building blocks, you can build a lot of different things. Now, this leads to a significant cost reduction and that in the prototyping, and that is because if everybody designs in the same process, then during the development phase you can combine a lot of designs from different users for different applications on one wafer. And usually in the first phase you don't need all the chips on a wafer. These can be hundreds, and usually you need only a few chips, and you see what you did wrong, you correct it, and you go for a new design. And in this way, by combining a lot of different designs on a wafer, you can share the costs of the wafer run, which are fairly high, over 10 or 20 users, and that makes it dramatically lower the cost. So this is an enormous advantage. On the left you see the first silicon electronics multi-product wafer. It was done in 1979. Link Conway is the name connected to it. And at the right side you see one of the first MPWs that we did in indium phosphide. It was in 2007, where we also combine a lot of different indium phosphide designs on a single wafer. Well, if you have a process that supports all this complexity, then it's very important to have good design tools. What you need is physical simulators, you need circuit simulators, you need mask layout tools. But once you have this standardized process with building blocks, then you can put a lot of the knowledge in a design kit. And that's done by the foundries. They know their building blocks and they provide the information about the building blocks in the design kit. And as a designer, you can select the components that you need, connect them to the simulation software, and in this way you don't have to feed in all this information yourself. You don't even have to know all the details. You can use it in a simulator without knowing all the details. Well, here you see an example of how it works. So, for example, you see at the top the symbolic picture of an AWG. You can select it from the list, and then dependent on the fab where you work and with which you work and the design kit that you use, it can be translated into different AWGs. They look different, they have the same functionality, so you see that in this way you can transport even designs from one platform to another. So, summarizing, the design kit is an extremely important part of the whole foundry system, and the contents of the process design kit, it is the mask layout, it are the design rules, so there are checks built in that you don't space your components too close and other errors that you can make. And very important, there's a library of validated components, so you don't need to reinvent the wheel every time you need a laser. You can take the laser out of the library, and the library has layout information, simulation models. And what's very important is also it has templates for packaging, so that once you made your chip, you can also use a standard package to package it. This is a chip explaining the cost advantage in using generic technology. It shows three different fab models. So in the vertical fab model, the fab and the process is owned by the company, and the largest investment is then in the clean room. For indium phosphide is typically in the order of 100 million euro or more. For silicon it's even more. And well, in the graph you see how many chips you have to make, how many square millimeters before the cost of a chip is at an acceptable level. It's in the order of 100 million. After the turn of the century, a number of fab owners opened their fabs for so-called fabless users. And that brings a large advantage for the fabless users. because they don't have to pay this expensive fab. They can start with developing a process for their component in the fab owned by somebody else. So then the cost goes significantly down, but developing a process for your components is still something that can be in the order of €1 million if you include the qualification. But you see, if you start with such investment level, then already at levels of 100,000 to 1 million square millimeters, the cost gets reasonable. Now the generic foundry model goes one step further. The process is standardized now. And so you don't develop your own process, you use a standardized one. And with that process, you can share the cost of that, so you are left and only with the cost of a design, which are typically in the order, well, maybe a man-year, €100,000. And in this way, you can get already a decent chip cost at volumes between 1,000 and 10,000, and that's for small companies a very interesting and attractive number. So the advantages of the open access foundry model are you can do rapid design if the PDKs are powerful. You have the cost sharing in the MPWs. An advantage is you design in mature technology, so there are less problems. And you can rapid scale to volume production because you design in an industrial process, and once you like your chip, you can order 1,000 wafers of it in the same process. Well, to do all of this, you need the foundries, but you need more. Actually, you need a whole ecosystem to support that. And in JEPIX, we are organizing this. So this picture shows the most important stakeholders. It are the foundries and also the packaging companies. But, well, most important, of course, the users with their applications. But most of them are not able to design a chip. So the third category is the category of PIC designers. They can translate the requirements of the users into mask layout. And so these three together, they form the ecosystem. And JEPIX has as partners the foundries and a number of packaging partners. Also for the software, it has a number of software providers and design houses as partners. And together we try to provide users with all the information they need and the help that they need to make these chips. Then there is in Europe also the Photon Delta organization that connects to the users and that tries to get as many users as possible, bring them in contact and help them with using this technology. And Photon Delta and JEPIX together, they form and they try to build and expand this system. So JEPIX is doing then the brokering. And you see here the JEPIX roadmap. You can download it from the website. Here a few examples of photonic ICs. This is what we developed in indium phosphide and triplex. So you see we made more than 350 designs already in the past years, in terahertz and RF circuits, optical data handling, optical switching. We made a variety of lasers, pulse lasers, tunable lasers, chips for medical and bioimaging, to photomicroscopy, microwave photonics, beamformers, sensor readouts are very popular, and also chips for fiber to the home. I have a few examples. I will go quickly through it just to give you a flavor of what is possible in these foundry processes. This is a tunable ring laser. It has 3 Maxine filter stages which you can control to control the wavelength, and you can tune it over 60 nanometer with a very decent side mode suppression ratio. It was made in the platform of Smart Photonics, and this is a ring laser made in the same platform. It can produce sub-picosecond pulses with a very broad COM spectrum. Here a quite different one. It's a 100-channel spectrometer. It contains 11 AWGs who separate the 100 channels, and it contains 100 detectors at the edge of the chip. It's made on the Fraunhofer Heinrich Hertz platform. Here a number of, here 2 WDM transmitters. On the left, a 180 gigabit per second WDM transmitter, which has 6 channels of 30 gigabit per second each. Was made on the Smart Photonics platform. And at the right, chip made on the Oclaro platform, 320 gigabit per second, 8 channels, 40 gigabit per second each, on a chip of 6 by 6 square millimeters. And this one has been designed for a standardized package, which is now underway at Tyndall. These chips have record high capacity density, 10 gigabit per second per square millimeter. So you see what you can do on those platforms. You can also do more academic stuff. This is an integrated microwave photonics filter made at UPV, and it has been the University of Valencia, and it has been published in Nature Photonics recently. And here another interesting academic application, a quantum entropy source made by ICFO and made on the platform of the Fraunhofer Heinrich Hertz. But there are also commercial applications, and they are increasing. This is a 100 gigabit WDM transmitter developed by Effect Photonics, contains 10 tunable lasers, 10 modulators, an AWG multiplexer, and a booster amplifier. And it has been made a chip of 4 by 6 millimeters. It has been made in a slightly customized generic process on the platform of Smart Photonics. And here another one from the company Technobis. The company Technobis is selling fiber strain sensors used in airplanes, for example in Airbus and Boeing, for measuring the deformation of the wings. They have a system, it's a box like this, but they moved to integrating it in a photonic chip. You see it at the left, the top left, and with this photonic chip the box was reduced to this size. It weighs much less, it is cheaper, it is better, so it illustrates the advantage of photonic integration. The last example is a hybrid application from an indium phosphide and a silicon nitride chip. So the amplifier, there's an amplifier in indium phosphide. There is a long cavity and a tunable cavity in a triplex chip. And by putting them together, you can make a very nice tunable laser with a very low line width with it. So this is what you can do in these generic platforms and how you can reduce the costs. But once you reduce the cost of the chip, it becomes more and more important to reduce the cost of packaging, because usually they are larger than the chip cost. And we have been working on that in the Paradigm project. So here you see generic package. We started with that, and the idea is that you standardize the position of the ports. So what we did here is at the top put 8 RF ports. At the sides we put 1 or 2 rows of DC contacts, and at the lower part the optical ports at the pitch of 250, also a template with a pitch of 25 micron. And in the area between the ports you can design your chip, and if you connect it to those ports, then once it has been made, it fits in a box which is made for this connection. So that's the concept of generic packaging. And here you see a package that we developed. It was developed by Oclaro in cooperation with Gooch and Hausago, and it's a Kyocera package 1 by 1 centimeter. In the middle you see the chip, and you see the DC and the RF contacts, and a silicon lens for connecting 12 fibers. At the moment we are working on integrating the 320 gigabit per second 8-channel WDM transmitter in this box, and that will really be a record amount of gigabits per cubic centimeter. Well, generic packaging is important, but also generic testing. The concept that we use for generic packaging is that you design for packaging. In the past, people did it the other way around. You make the chip and then you design the package. That's the wrong way. You have first to design the package and then design your chip such that it fits. And you do that by standardization of the interfaces and by including the packaging templates in the PDK. And then if you make your test equipment compatible with the packaging templates, then you can also build generic test setups in which you can very easily mount your chip and do the testing. So that's also important. And JAPIX, in combination with the PIXAP pilot manufacturing line for packaging, which is run by Tyndall, we are working together on creating open access to such generic packaging test facilities. One slide on the history of the photonic foundry model. So in Cobra we started already at the turn of the century with developing these generic processes, And an important step was in 2004 the start of the EPICSnet Network of Excellence. It was a European project. Roel Baats from the University of Ghent and myself, we were the coordinators of that project, and there were more than 50 groups working in integrated photonics involved. And the theme of that Network of Excellence was shared access to expensive infrastructure like clean rooms and like expensive measurement setups. An important thing was in 2007, then the steering committee of EPICSnet came with a vision document in which it recommended to start to transfer the foundry model from electronics also to photonics. And it recommended to start foundry platforms, and we did that. We started with 2 fabrication platforms, one in silicon photonics. It was EPICS Fab, later taken over by Europractice, and it was the JAPICS platform. And both platforms managed to get big projects funded. For silicon photonics, it was the Helios and the Platform M. For indium phosphide, the Europic and the Paradigm projects. And in those projects, we improved the technology, we created design kits, we worked on the packaging. So in this way, it started in Europe. And a little bit later, we also started the 3rd platform on silicon nitride. It was a triplex platform run by Lyonics. Well, then in the US, it started 2011 with the OPSIS broker from Michael Hoogberg. I think he did a very good job, worked with a number of foundries. I think the most intensively with the IME foundry in Singapore. And he developed a very nice design kit. Unfortunately, that program was stopped in 2014, but fortunately, the US is now has now started a big effort on foundry, on creating a foundry infrastructure with AIM Photonics. So that's about the history. Then a slide about technology comparison. The 3 most important technologies is indium phosphide, silicon photonics, and silicon nitride. Well, you see silicon nitride is very good in passive components, has a very low loss, but in all the other building blocks, the lasers, modulators, switches, optical amplifiers, and detectors is not so good. It's perfectly complementary to indium phosphide. That's not so good in the passives, but it is very good in all the other components. And silicon is somewhere in between. It has very good detectors, very good switches, but the modulators and the lasers, there's a lot of improvement, but they are still significantly behind the indium phosphide laser. So if you see this table, you might wonder why silicon photonics is so popular. Well, I think it's not because of the performance of the building blocks, but it is because of the access to large-scale silicon fabs. And there you have high-performance manufacturing. That doesn't mean that the component specs are high performance. They can be modest, but what is very important, they can be realized with a high reliability and a high reproducibility, and that's important for your design. And they have lower chip costs. They offer lower chip costs, but that picture is a bit complicated because if you look now to the MPWs, then you see that indium phosphide MPWs offering more performance and they are cheaper than the silicon one. That's what you wouldn't expect. So my next slide is on the cost picture, and what you see here is how chip costs scale with volume for different fab sizes. So the colored lines are indium phosphide fabs, a 3-inch, a 4-inch, and a 6-inch fab. And the dashed black line is an 8-inch fab that could be a small silicon photonics fab. Well, as you might expect, for small aggregate volumes, so on the horizontal axis, we have the yearly number of chips realized in the fab. For small numbers of chips, the small fabs are cheaper because the investments are lower. But if the number of chips increases, then the large fabs get cheaper. And once your fab is completely filled, then you can offer also at that lower price for smaller customers. So that's for the silicon photonics fab. If they run in a silicon fab, you can offer, you also have the volume from the electronics user, so you can offer at a fairly low price. So it's depicted here. Well, it might be dependent, of course, on the specific chip and application. Now, in indium phosphide, if we design in a 4-inch fab, that level is higher. So indium phosphide is a few times more expensive, but that's not a complete picture, because in silicon you also need a laser, and that's an indium phosphide laser. It will cost something, and you have the assembly and packaging cost. Now in indium phosphide you also need some assembly and packaging, but maybe a bit less because the laser is already integrated. So in this example you see that the indium phosphide ends up a bit more expensive than the silicon, but it offers more performance, so it's a trade-off and it depends on the application what is the best choice. What is interesting is, if we move from 4-inch to 6-inch, then the cost of indium phosphide will also scale and go down, and it will become more attractive. So you see there, it's a complex picture. You have so there is no single solution for all, and you have to look to the specific application, what is the best technology. And this complexity is also reflected in this market prediction from the light counting. What you see there is that at the moment the market for the transceiver market is completely dominated by indium phosphide. Mostly at the moment discrete components, but increasingly indium phosphide peaks. But also in the coming year the prediction is that indium phosphide will dominate this market, but you see also that silicon photonics is rapidly growing, so there's clearly a market for both. Well, this situation inspired us on this cartoon. You recognize the story of Tom Thumb, and the 7 lead boots. The story is that Tom Thumb stole the 7 lead boots from the big giant, and with those 7 lead boots he could run faster than the giant. And well, the analogy is clear. The small guy is indium phosphide, the big guy is silicon, and indium phosphide stole the methodology from silicon electronics. So we used this generic integration technology, and with that technology, in some respects, we can run faster than silicon. But it's not the end of the story, because silicon and indium phosphide will come closer and closer. For the next years, the integration of photonics and electronics is really key to the development of photonics, and you can do it in different ways. In Eindhoven, we work on integrating indium phosphide photonic layer on top of the CMOS electronics, but you can also do it in other ways. We will see what will become the best method, but it's clear that in the future, the happy end will be that we will have both indium phosphide and electronics, and maybe silicon photonics, we will see, but it will come all together, and there's room for all of us. Thank you for your attention.
Well, thank you, Meint, for sharing your insights and innovation. We look forward to seeing the way your research and work takes you. Now, please welcome the President of the IEEE Communications Society, Harvey Freeman.
Good morning, everyone. The IEEE Communications Society, or ComSoc, is currently the 3rd largest society with about 32,000 members in the IEEE. The IEEE itself is made up of some 40 societies and councils and has about 425,000 members currently. In January 1963, the American Institute of Electrical Engineers, that was founded in 1884, and the Institute of Radio Engineers, founded in 1912, got together and formed the Institute of Electrical and Electronic Engineers, which now is just known as the IEEE. The Communications Society was formed from a group on communications technology in 1971, and on January 1st, 1972, became a full society of the IEEE. This is the 65th anniversary of the Communications Society. The first president was Albert Culberson, and I am the 23rd president. The Society currently operates with 21 voting members that are members of our Board of Governors. We are heavily involved in the communications area with our many conferences, workshops, symposium, technical committees, publications, and standards activities. Our conferences embrace cutting-edge technology at ComSoc-sponsored global events, Every year, thousands of participants come to discover new ideas, explore innovative solutions, and network with the leaders who are changing the world of communications. Our workshops and symposium, on the other hand, provide small, intimate settings and a relaxed ambiance where participants can concentrate on technical interchange with their colleagues and enjoy some unique social events and experiences. Communication standards enable the global marketplace to offer interoperable products and services at an affordable cost. Standards development organizations bring together stakeholders to develop consensus standards for use in our global industry. Because of this, standards are extremely important to the work and careers of communications engineers, an important part of ComSoc's efforts to bring more practitioners into our society. What is new with the Communication Society going forward is our work with IEEE initiatives. We are trying to develop these new areas covering multiple societies as major interests and work. Foremost currently is our Internet of Things initiative that's made up of 7 major societies, like the Communication Society, Signal Processing, Communication, Consumer Electronics, and 4 others, and 10 minor contributors, the Power Society, Industrial Electronics, and 8 others. Meetings, conferences, and Internet of Things, a magazine, and other related offerings are already in the pipeline. Other initiatives that we are working on are 5G, green ICT, smart cities, smart grid, and fog computing. All of these now involve multiple societies. There's no silos anymore. This is communications, this is computing. All of the different work that we see being done today involves all different technologies and different societies and councils. To telephone communications advances in 1962 to today's gigabit transmissions, wireless phones, miniaturization, and other technological advances, our communication society has been a major contributor. We are now looking forward to be parts of these types of game-changing advances by our 75th anniversary. Speaking of game-changing advances, it's a privilege each year to recognize optic innovators and industry leaders each year through the awards program. Later today, the IEEE Communication Society, the IEEE Photonics Society, and the Optical Society will hold a special award lunch, honoring this year's game changers who are this year's recipients. Thanks to the generous support of Corning, we will be able to recognize these outstanding individuals more in depth later today at the awards luncheon. But I'd like to take a few moments this morning to congratulate them. You can see some of the award winners running on the screens, and you can find the full list of award winners and honorees in your programs, along with their citations and other details for each award winner. Congratulations again to our award winners. Next, we will recognize members of the 2017 Fellows class for the IEEE and the Optical Society. The IEEE Photonics Society Fellows being honored are John Boleto, Chris Cole, Joseph Ford, Shan Liu, Shu Namiki, Edogan Ozkan, Seb Savory, and Eric Swanson. The IEEE Communication Society Fellows being honored are Shu Lang, Shan Liu, Shu Namiki, and Seb Savory. The Optical Society Fellows being honored include Gabriel Bosco, Walter Buell, Wayang Chen, R.F. Chaudhuri, Ivan Georgievic, Po Dong, Andrew Forbes, Yang Wang, Hong Lu, Malin Permanente, Leslie Rausch, Seb Savory, Perry Ping Shum, Kathleen C., Lian Shenyan, and Shin Lang Zhang. Congratulations to our new fellows on our outstanding achievements. In addition to the fellows recognition, In addition to the fellow recognition, there are 3 other awards presented during this luncheon. The OSA Tingley Lee Innovation Prize will be awarded to Tetsuya Hayashi. The Charles Cow Award for Beck's Optical Communications and Networking paper will go to Mayor Chanagoda, Riza Nijabadi, and Dimitri Simeondu. And this year's Outstanding Student Paper Award competition, the grand prize winner is Z. Lee from the University College London, with honorable mentions awarded to Michael Thurer from Fraunhofer Heinrich Hertz Institute and Zainab Zanjabi Eznave from the University of Central Florida. Finalists include Ketor Beniyaha from Nokia Bell Labs, Rafael Puerta from the Technical University of Denmark, and Jiang Wang from Georgia Institute of Technology. And finally, the paper selected as the winner of the Journal of Light Waves Technology 2015 Paper Award is Monolithic Silicon Integration of Scaled Photonic Switch Fabric, CMOS Logic, and Device Driver Circuits by a team of researchers from IBM, Elenion Technologies, Instituto Tecnológico de Costa Rica, Global Foundries, the University of California, and the University of Illinois. Congratulations to all these outstanding individuals and their achievements, and I hope you'll forgive me if I mispronounced your name. Now I'd like to bring up Andrew Lord to introduce this year's final speaker.
Thank you, Harvey. Congratulations again to the IEEE Communications Society on 65 years, and congratulations to all of our award winners this year. Well done, guys. So we come to the final speaker this morning, and just to introduce Mischa Dohler. Thanks to advances in optical communications, the internet is accessible from nearly anywhere on the planet. It allows users to check emails, watch video, share photos, and stream music. But what are the next steps going to be? For example, how close are we to having a doctor able to perform surgery a continent away from the patient? What's required to get over that next technological barrier? These are the kinds of questions that the next speaker has made the core of his work and of his research. So Mischa Dohler is full professor in wireless communications at King's College London. And he drives a kind of cross-disciplinary research and innovation in technology and sciences, and even the arts. His work and research have resulted in pioneering practical aspects of cooperative communications. He's made substantial contributions to the fields of tactile internet, 5G systems, the Internet of Things, and smart cities. His work has resulted in more than 200 highly cited peer-reviewed journal and conference papers. Dohler introduced the concept of the Internet of Skills, which enables skills to be executed remotely using cutting-edge technologies such as tactile internet, artificial intelligence, and haptic encoders. He's also the first to introduce cross-disciplinary co-design into the 5G development framework. But his original ambition growing up was to become a professional pianist. And in fact, Dohler has already released 4 albums on iTunes, and this morning we will be privileged to hear some music from his 5th album. He's been a featured speaker at numerous conferences through Europe, including the International Conference on Communications and the Wired Conference in London. He's also been a guest on shows like Ian King Live on the Sky News Channel and interviewed by outlets like the BBC and the Wall Street Journal. He's a Fellow of the IEEE, the Royal Society of Arts, and a distinguished member of Leaders Excellence at Harvard Square. His presentation today will focus on the disruptive technology approaches in wireless 5G and next-generation optical networks, which will allow us to break through that next technological barrier. So I'm really thrilled that he's joining us this morning, partly because he's a good friend, but also because this promises to be a fairly unique OFC plenary presentation. So I'd like you to join with me in welcoming our final plenary speaker this morning, Professor Mischa Dohler, and his presentation, Internet of Skills, where communications, robotics, and AI meet. Thank you, Mischa.
Good morning, yeah. Good morning, ladies and gentlemen. Now, the internet has come a really long way. It took us decades to build, and we have now every single computer wired up on this planet, and we got every single smartphone connected, and shortly we will have probably trillions of devices in that internet. So we transited from a fixed internet to a mobile internet, to a things internet in the end of the day. And I think it's a very timely question to ask, what's next? What is the next big internet for which you provide an infrastructure? And I got my inspiration a few years back, and that was at the midst of the Ebola crisis, where King's College London was leading UK's response down in Sierra Leone. And we got some really hands-on knowledge what was going on down there. It was a situation of desperation, really, and mainly caused by a total lack of medical skills down there. So I thought, why can't we combine our cutting-edge robotics with cutting-edge networking and a bit of really good AI and build an entirely new internet? An internet which would allow us to virtualize skills and transmit it from any point on the planet to our crisis areas. Now, I've worked on that concept for a while, and I gave it a name. I called it the Internet of Skills. And I thought, once it's up and running, maybe in 5 years, maybe in 10 years, it would democratize labor exactly the same way as the internet has democratized knowledge and information. It would change the way how we engage, how our industries work. I could teach somebody how to play the piano, and somebody could teach me how to paint. And you will wonder, how is that internet of skills, different to the internet we are designing, such as Industry 4.0? Well, the biggest difference, in my opinion, is I have the human in the loop. Because humans love humans in the end of the day. And despite our ability to automate everything we could probably automate, I don't think humanity's roadmap will be Industry 4.0. It will be rather something what I call Human 4.0, the ability to amplify our skills by means of machines and AI, but not replacing the human. And you know, that observation, I got it after a very fascinating conversation with a very good friend of mine who happens to be one of the most senior pilots in British Airways. And he told me, Mischa, you know, we could have flown airplanes 20 years ago fully automated. Taking off, flying, landing, it's a really easy thing to do, and we would have had 10 times less accidents. We understand that. But he says, the only reason I'm getting into this cockpit every morning is because if I didn't, you wouldn't fly. You wouldn't trust these machines to bring you from one end of the world to the other. Right? And we essentially as humans trust humans to execute the job. And I think we will face actually the very same challenge with self-driving cars. Self-driving cars, let me just, take this moment here and query this audience right now. Hands up, everybody who would dare actually to sit in a self-driving car, turn around, and work whilst the car is driving you at 120 miles through the city. Hands up. Be honest. Now, I have a very good photographic memory. I'm gonna catch you in a few years' time. I have you on my radar. But you have seen what I've seen, right? It's just a few arms really have gone up in the end of the day. And we need something where the human actually could interact. So we work with the Transport for London on a concept called driving as a service, where in very precarious situations, actually humans would take over the driving. So that's from one end. On the other hand, you will say, building an internet which allows me to transmit skills through touch and for kinesthetic movement, muscle movement, has been done before, right? All of us has been exposed to this in one way or another, and the answer is yes, and the answer is no. So we do have that equipment, and you see some of that here in the corner. It is a Da Vinci robot used at King's College London to do robotic surgery. It is there. Okay? It is a no because we are not there yet where I want this network to be. And to exemplify this, I brought up the evolution of the internet because that's an evolution we all understand. Let's zoom backwards 50 years. If you were lucky, you had a Siemens video phone, right? But to communicate with somebody on that video phone, that person also had to have a Siemens video phone. And if you're lucky, these phones were communicating over a circuit switched link. Most of the time it's probably still manually switched, right? Now, zoom forward 50 years, we have done a lot of research, a lot of innovation, and I would like to highlight two. We have worked on the network. We introduced IP and all that great infrastructure which you guys have been designing over the decades. And something else we did, we came up with codecs. And these codecs, video and audio codecs, allow me today to take a video on my smartphone and play it on my Dell computer. We take that for granted, but what it actually enabled us to scale the edges and bring down the costs, and essentially underpin an internet which is driving parts of the economy of this part of the millennium, right? So with the haptic networks, I'd love to do that very same transformation. Drive it out from something which is really a propriety, right? Something where a Da Vinci only works with a Da Vinci. A General Electric sensor only works with a General Electric actuator. ABB, Siemens. I want to break these out of the silos. And I want to scale it and bring the costs down. And there are two things we need to do very urgently, and we can't do that over 40 years. We want to do that quicker because we know what we need to do. And the first thing is we need to come up with a really good network, ultra-low latency. I'll come to that in a moment. But we also need to come up with codecs, with new haptic codecs which are able to understand each other's technology. So this glove here, this tactile glove from NeuroDigital is able to talk to a General Electric actuator. This is where I would like this network to go, and therefore build a truly standardized Internet of Skills, enabling these service economies at scale. Now, what do we need from a tech point of view? Well, that's what you see. It's very simple, really. You see on one end one or several human operators communicating through one or several networks and reaching one or several slave devices which are performing a certain task. That's what it is. Now, the fascinating thing is if you want to transmit touch, like I have it on this glove here, you actually do not need a network which is very low delay, because touch is something we have a lot of latency on. It takes about 120 milliseconds between me touching the end of my finger and that actually reaching my brain. So the really interesting thing comes in when I start to move things. Kinesthetic muscle movement. I want to execute something, do an operation, I want to move a box, I want to do something on the other side of the planet, and this is when you need an ultra low latency network, because action and reaction has to happen within about 10 milliseconds. Right? If you don't do that within 10 milliseconds, systems become unstable, and we as humans also become what we call cyber dizzy. So here we are. We have advanced now quite a bit in terms of the technology, and let me start with the haptic codec. So I've personally insisted that we ramped up within the IEEE an entirely new standards group which only deals with an haptic codec. Again, I'm trying to break the silos here and make sure that future equipment can talk to each other without any problems. So please join that standards group if you are interested in the work. It's IEEE 1918.1. We have also advanced the AI. You need quite a bit of AI. We call it model-mediated teleoperation system. And what we want to do here is to have the slave side predict what the actuation side, the human, is going to do, and the human side predict what the slave environment is going to do. So the action and reaction is being predicted on both ends using advanced artificial intelligence. Now, we don't need that prediction over seconds. We need that prediction over maybe 10, 20, 50, 100 milliseconds. And the reason is because we want to stabilize it. Remember, I'm not building a local area network. I'm building an internet. It has to work from London to Los Angeles and back. Speed of light is one thing we can't beat, so we need these type of AI systems to stabilize the delay. And then the network, well, that's why we're here today, really. This is our cup of tea as a community, and on the wireless edge, we're working very much on what we call the tactile internet, which is an ultra-low delay wireless interface, which involves 5G, but also more than that. And then we have the optical network, which you guys represent. Now, let me do a deep dive on the challenges. So the biggest challenge, arguably, is delay. I explained it. Delay is really driving these type of Internet of Skills applications, and there are four constituents of delay: the speed of light, the serialization delay, then there's a congestion in the buffers, and there's the application layer delay. So all of that is needed because really what matters is the delay from application to application, and the constituents are right here. Now let's look at the different scenarios. You see here the human vortex type of reaction is about 10 milliseconds. So the time it takes for my eye to take a visual signal, process that, and stabilize the image. And that's our reference point, because if I want to have the human in the loop, I need to be running on these 10 millisecond cycles, right? So that's what we have there as a calibration point. Industrial local area networks, Industry 4.0, we are there. We can do 10 milliseconds today, and hopefully 5G will enable also part of the wireless connectivity to enable the 10 milliseconds. Now, what about a poor metropolitan area network with a lot of serialization switches, etc.? So you get now a delay here which can't handle the 10 milliseconds anymore. Let's put now an application on top, such as video or anything else you really want to put on top, and do a connection between the UK and, let's say, Frankfurt and Germany. Now you see delay, speed of light is still negligible. It's about 3 milliseconds, but the buffer and congestion delays are very high. We can measure that using internet tools, and of course application is introducing a massive delay. Now let's drive this further and say, hey, can we connect London with Los Angeles using the type of Internet of Skills applications on top? And here's where we really struggle. Speed of light, it's nothing you can do about, a lot of congestion on the way, and the application's introducing again a massive delay on that. As I said before, the model-mediated AI can essentially bring down that delay by about 100 milliseconds to stabilize that, but we're still a very long way to go. So if you guys could help us with the buffer side, with the congestion side, and ideally do, you know, a lot, if not all, the routing actually at optical layer, not in the RF kind of switches, so literally the routing is done in an optical domain, that would be a great value add, because we could forget about the yellow boxes pretty much immediately. So it's one of the homeworks I'd love to give. I know it works in the labs, but I'd like you to make it commercial. The other challenge is on the application delay, really, and it becomes very quickly a bandwidth challenge. And I want to exemplify that by using video. So any of the modalities you would transmit in the Internet of Skills, video would always be there. But now the video is not like Skype. We didn't have 200 milliseconds to do that. We have to do really 10 millisecond type of stuff across the planet. Now, how do you do that? Well, you struggle really to use a traditional type of encoders because the video encoders take a lot of time to do the encoding, partially because the hardware isn't powerful enough, partially because they need to look into some subframes coming later in time to do a perfect encoding. So you can have hardware today to get you a very good video compression within milliseconds, but it's very expensive. Remember, I'm trying to build an internet which is cheap and which scales. And the edges will always go as cheap as possible to bring essentially the problems back to you as a community and come up with a good network. So therefore, to bring down the delay, the only thing we can do is just don't encode it at all, right? So what CMOS comes out of the CMOS cameras, it's being unencoded, transmitted over the network. Once you do that, your data traffic just really goes through the roof, right? So a high definition full HD video normally would consume at 10 megabits per second, suddenly becomes 100 megabits per second. Something which is, you know, my 8K video, it's about 100 megabits per second goes to a gigabyte, and I don't want to talk about virtual reality. We'll see something later on. You can talk to Richard about this later on. Gigantic data rates being pumped forth and back in the network, right? So, and here's a problem, because a lot, if not all, the predictions I have seen on the internet traffic evolving over the years, the famous Cisco predictions, they assume these video codecs to work on these 100 millisecond horizons to give us a good compression. Now, if you just take 1% of the future internet traffic to be uncompressed, suddenly your rate is double. If you take 10%, suddenly your rate is 10 times more. So there's a huge data flood coming here, which isn't following the traditional prediction from Cisco. It's actually an order of magnitude above this. What I'm trying to say here is that you have a lot of work to do to help us to essentially get around that. Good news, right? But we're fighting our own challenges, really, in the wireless community. And I want to underpin that with what we call Cooper's Law. So Martin Cooper, one of the pioneers of mobile telephony, he established that capacity on the wireless edge doubles approximately every 18 months, and we managed to boost that capacity over the last 35 years by a factor of 1 million. Now, if you zoom in, and this is a little bit of an untold secret here, the physical layer has contributed by a factor of 5. The spectrum we're using has contributed by a factor of 25. And fasten your seatbelts, it is a smaller cell which has contributed by a whooping factor of 1,600. 1,600 by simply making the cells smaller, right? So if you see that and you compare that to the physical layer has an impact of 0.3%. Why do we bother to dispute if we should use LDBC coding or turbo coding? You see the problem? Right? The problem is elsewhere. We as engineers got stuck in the physical layer trying to come up as closely as possible to the Shannon limit, where the problem was actually in a totally different field. Now, if it's an architecture problem, then suddenly you can do a lot more things. So one of the concepts we pioneered at King's College London is the notion of the decoupled up and down link. So when you do your phone call today, the up and the down link come from the very same base station. Now we said, hey, if really small cells is the future and it's going to get smaller and smaller, there will be loads of those. Why do we need up and down link on the very same link? Let's decouple that. So we figured out that having the downlink from a macro cell and the uplink to a micro cell here in the room fundamentally changes the dynamics in the system. Capacity goes up by order of magnitude, and above all, reliability and stability improves by a factor of 10, if not 100. Right? So with that type of ability, we suddenly need a very strong optical network because we need the front haul to manage all that decoupled layer 1 or layer 2 type of traffic. Right? So again, what I'm trying to emphasize here is a lot of work on the horizon which comes due to the decoupled architecture. Right, so where are we today in terms of deployment? Well, we felt that as a community we are ready to play. We are ready to deploy pre-commercial and commercial, and we said, hey, let's do something really bold and build maybe the world's largest end-to-end 5G system in the United Kingdom. And it's a pioneering development which has been founded by 3 partners. The first one is the 5GIC University of Surrey, and you see here Professor Rahim Tafazoli, who has been absolutely instrumental in bootstrapping that relationship and enticing the UK government to loosen a lot of money for these type of developments. We also have Bristol, University of Bristol, and Bristol is open in the game, and the sole and the really pioneering heart behind this is Dimitra, who is sitting right here in front of me. She has been also instrumental in coming up with a lot of the pioneering visions of that concept. And then there's my 100 People Center in London working on the 5G and big data story. Now, what we're trying to do here really is, first of all, each of us has their own little sandpit. We're rolling out 5G stuff, including mobile networks, a core network, as well as the fixed network. We're going to trial the 5G radio interface on the 3 pioneering bands. That's 700 megahertz, 3.5 gig, and 26 gig. We are ramping up totally new front hauling technology, Cloud Run with functional splits, and on the networking side, core network, we do a lot on the super convergence between Wi-Fi as well as 3GPP technologies. So we want to bring this out, partially our equipment, universities' equipment, and it's partially going to be also the vendors' equipment. And the next thing we want to do is we want to connect it, and we're going to use something which Dimitra pioneered, an ingenious idea to use something what we refer as, or she refers to as the SDN switch. Imagine it being like a marketplace between SDN connectivity and policy frameworks where we can bind in any type of partner in a totally flexible way. It all meets in SLAO, which is our high computing and high speed network in the United Kingdom. Right? So what we want to do next is also we want to bring in third parties. We want to bring in more universities, more vendors, national and international. So if you want to participate in that, if there's anything you would like to test in a real environment in downtown London, on Bristol, or on Guildford, please drop us an email either or to Dimitra or myself or to Rahim, and you're most welcome to participate in that. Right, so let's look what we're going to do with that, because the ultimate question remains, why do we do all that technology? And I'm showing here some graphs, so really the truth is there may be three reasons why we're doing all that. The first reason is we want to have a lot of fun. Right? We want to celebrate science, we want to celebrate technology, something we do far too little. So I'm trying very hard to get my staff involved in real projects in London with the National Theatre, the Royal Opera, with the ops centres in London, the Transport for London, etc. So they get a hands-on experience on what's going on out there. The second thing we want to do is, I want to make sure that we involve all these industries which are going to be using our technology in 5-10 years' time, will not question the cost, and they will appreciate the value of the technology delivering whatever needs to be delivered. So involving them very early in co-designs is absolutely instrumental in making this happen, right? And the third thing we want to make is really transform these industries, make them 10 times better, make them really competitive, make them very attractive. That's what we're really trying after. So, you know, I started in London with a few industries, those which either King's is very interested in, very good at, London itself is very good at, or in general, it's an industry which just couldn't miss. So you see a few examples here, like cities work a lot with Transport for London. You see the gaming community. So we just demonstrated at the Mobile World Congress a mobile edge cloud and a virtual machine which is migrating in handover procedures through London, where all the heavy graphics rendering of these next generation games is done in the cloud and being streamed down like Netflix on your small device, so you can have high-end PlayStation 4 and 5 games on very low-end devices. We have demonstrated that, and arguably the more interesting one on the arts and on the health sector. So you see here on that slide, you see Prokar, and he's operating. He's a pioneer in robotic surgery. Robotic surgery means it's not anymore the surgeon who's doing the operation. It's actually a robot which goes in the body on a very, very small keyhole. The operation itself takes a little bit longer, but you don't lose any blood. So the patient, instead of recuperating for 7 days in the hospital, can go home pretty much immediately. So it's a huge business case to the healthcare system in the United Kingdom and around the globe. And Prokar is luckily a professor at King's College in London. King's owns 4 hospitals. It's very easy for me to communicate with him and say, hey, let's do something together. And he gave me homework. He said, Mischa, solve me 3 problems. Problem number 1 is, when I do the operation, I can't feel. Because before, when I was literally in the patient, I could feel. Now I can't. There's a metal rod in there. Second thing is, if I could operate from a North London hospital whilst the patient is in a South London hospital, that would be great, because the commute through London is killing me. And the third thing he said, please help me with the training of my staff. It comes back to the Internet of Skills. He can only train 1 person after 1 person. If that person isn't good enough, 2 months have been in vain. If we could digitize that skill of the operation, we could save it in a database, and we could actually replay it a little bit like Netflix anytime we want to do that, right? So that would be a big thing. So we did it. We just built the whole thing. We essentially gave Prokar the feeling of touch, the ability to do the operation remotely, and record the skill set needed to do these medical operations. And we had a great Mobile World Congress where we demonstrated that. And there were a few world's firsts, really. One of the world's first was we developed a sensor, my adjacent robotics department at King's, a sensor so susceptible it would actually detect cancer 2 centimeters under your skin. right? So you as a human, no matter how susceptible you are, going over the skin, you can't detect it. That sensor can do it. It's kind of X-Men type of capabilities. So we did that, small sensor, very cheap, scalable to the billions, no problem. We also build in the touch thing. So that's a haptic glove here. You can't feel it, but I can feel it. I can feel things here. That glove allows me to feel rain, tissue, whatever I want to do. We connected that through a 5G real-time sliced architecture to really ensure that the stream is of highest quality between the two ends. And we brought in, of course, a virtual reality capability through Opto, which you will see later on here, the world's first real-time virtual reality. The stitching time, so between screen and screen, is less than a millisecond. Nobody has done that before. Normally the quickest you have like 3 seconds, maybe a second. We had less than a millisecond to put it all together. So give a fully immersive virtual operating theater to Proca, and he could execute these operations from anywhere where he wanted to. Now I'm going to show you a video and I'm going to talk you through some of these constituents. So what you see here is Costas moving the robotic arm and being in the operating theater with the VR equipment. That's a touch device, which was just here, the 360 cameras, the 6 GoPros, which we have on here as well. And you could feel essentially inside the body. Here's the body mock-up. There's a robotic surgery tool going inside the body. You see the sensor at the very end, very small miniature sensor, essentially picking up these signals, cancerous tissue at an extremely high precision, testing over the field, and people essentially being part of that operating theater. Very simple to use virtual reality kit, and here Costas, one of my staff members, really helping with the deployment. So it was quite a successful, really, Mobile World Congress for us, where we showed essentially the world's first remote operating capabilities of a 5G SDN sliced architecture. Right, so after we've done the medical, we said, hey, let's move on now to the arts. And that's very close to my heart. So you have heard that you know, my ambition was always to be in the music industry. Really, what we wanted to. When I joined the center in London, I asked my people a very simple question. I said, guys, what does it take to disrupt the performing arts world exactly the same way as Netflix has disrupted TV? If you think about it, Netflix has changed the way how we consume content. Today we can watch a film anywhere we want, on any device we want, at any time we want. But interestingly, and maybe that has escaped your attention, Netflix has also changed the way content is being procured. A series like Stranger Things has come up without going through the traditional Hollywood ranks. It's been, in a sense, almost a crowdsourced type of application. That's what Netflix has given us. It has empowered us as a viewer, and it has empowered the acting industry to essentially become a world player. Now, the question we ask is, could we do the same now in the arts world? What would it take to give a fully immersive feeling or experience to anybody watching opening keynote, Madonna playing, the opening of the Olympics? Could we virtualize audiences, real audiences? Could we virtualize stages with actors, real actors? Could we virtualize the musicians, some real musicians, bring it all together, create some new art forms? That's the big question we ask. If you look at the whole art sector, it's extremely conservative. It's actually one of the most conservative verticals I know of. It hasn't been disrupted since the times of Shakespeare, right? And arguably since the times of the Greeks. So I think it's time to do something with them, and of course we have tried as a community. Network performance has been tried for the last 20 years, but we couldn't really solve it, all right, because the network wasn't good enough, or the piece of art wasn't good enough. So we went together with Ali Hosseini, who's a really well-known American artist, with the National Theatre, with the Young Vic, and other really high-profile venues in the United Kingdom, and try to come up with something where technology and the arts are merged into one thing, right? And I could show you a video, but I decided to actually take it a bit further and do a live demo. Take the risk on that. In fact, it's a package. There are going to be 2 live demos today and 1 launch. So I'm launching my 5th album today. The record label just told me it's been distributed globally on every single music platform on the planet. So if you happen to be on iTunes, Music Play, or on Spotify, please follow me. It would really make my day in a sense. And so I'm launching that today officially, and I'm going to do that by essentially bringing on 2 pieces here. And the 2 pieces are going to be first a slow piece. It's Ouroboros. It's my opening piece of my 5th album. I composed it for Ali, who's been using it for his exhibition called Ouroboros. And I'm going to be using a haptic glove, which essentially is going to reproduce my movement on the piano. And you're going to see not only the rendered hand, you're also going to see the vector graphics of my skill vectors. So the ambition is to record that, store it, standardize it, and replay that in a sense on any piano or exoskeleton you want to use that. So the people who helped me really a lot on that type of project is Laura, and Laura is from Music for Mental Wealth. She's going to help me to put on that glove, really. 1 second, Laura, we're going to get there in a moment, right? So she's going to be using some of that technology in one of her really exciting ventures, which you're most welcome to talk to her about in the break. I'm also having Richard with me. He's the CEO of Opto, the virtual reality company. So if you guys maybe could start setting up this stuff already. So there's going to be the second part is going to be with our 5G slicing architecture. So first part is the glove. Second part is a quicker piece, which is called Timeless Memories. And I'm going to show you there 2 video streams, and I hope it still works. Sometimes it freezes. One stream is a 5G slice stream where you really have a total control of the buffer, so we can guarantee the slicing across the network. And one is the traditional best effort type of traffic. So let's get that going. I had to recompose that first piece in the airplane because I thought I'm going to be using this glove, but it turns out I was shipped on Friday a slightly larger glove. Yeah, good one. Which is thicker. So I had a lot of the keys essentially black and white and got stuck on the with the actual glove. Let me just put this up. We want to film that, right? So let's see if we can put this on. Are you excited? Yeah? So I have to say, I'm not a professional pianist, right? I'm an aspiring professional composer, which is very different, but here you go. We'll give it a shot, right? So why not? Okay, let's see, Laura. Yeah, so this one needs to go lower. Yeah, here. Right, okay, right. Is it on? Yeah, it should be on. A bit tighter, maybe. Yeah. All right, good. So now we need to calibrate that. If I could have the calibration on the screen here. Can you have a look if we can get it? Is it up and running? Oh, sorry, I need to log in. Type in passwords with thick gloves. I hope it works. Let me just have a look, because otherwise it takes too long. Yeah. All right. Good, Brent. So we need to calibrate that. Don't forget to bring in the vectors. Yeah. All right. So I hope this is how we did it. Yeah. All right. Could you bring in the vectors? Yeah. So what you see here is the is essentially the hand which is rendered. Sorry, can you move the cursor just to get it off? Yep. So what you see here is a real-time calibrated, graphically rendered hand. It's very volatile, so we may end up with the hand being out of the screen, but it's done in real time. And you also see the actual vectors, the skill vectors. Do you see how they move? Right? So that's being recorded in real time as well. So let's see if we can get this going. I want to have a memory too, so I'm going to record that on my own 360. Right, let's go. So I may get stuck in the keys, right? I'll see how that goes. Right. All right, so now the second piece, I hope the the two cameras, right? So what you see now is the real-time 360 virtual reality feed, which Peter is seeing whilst he is sitting on that chair here. I hope he doesn't get too dizzy. And we do have 2 video streams there where I see already one is frozen. I do apologize. That's what happens with real demos, right? So the one which is working here, right, is the real-time sliced virtual machine here, which is guaranteeing the path, in this case, emulated to go through London. And the other one is a best effort, which unfortunately already froze. So let's give it a try. All right. All right. Thanks. That's it.